We're now going to take a look at a combination circuit practice, and we're going to work all the way through it using the same value of resistors that we've been using so far. This time it's a series parallel, so we have R1 in series with a parallel combination. So the first thing I'm going to do is I'm going to draw my circuit over here. I'll go once again with 24 volts, and then this is a 1000 ohm. Going to be R1 is 1000 ohms, and then that is going to be in series with a parallel. So I draw these, I end up with, we'll go 4700 ohms here and 5600 ohms here. And then I'll just wrap it around like that. Okay, so there's a series, and then my parallel, and those are in series. So the first thing I need to do is rule 1, look for anything in series. I don't have anything. So now I'm going to look for something in parallel. I do. I have these right here. So these need to get simplified. So my circuit is going to become this, okay, where the first one, R1, still stays 1000 ohms, but I now need to get these two resistors simplified into a single one. And so how do I simplify two parallels? I have 1 over RT is equal to 1 over 4700 ohms plus 1 over 5600 ohms. Okay, so if I bring my calculator here, I'm going to go 1 divided by 4700 plus 1 divided by 5600. I'll hit equals. Okay, now I've got a really small number there, 0.003. Because it's a reciprocal here, I need to flip it. Okay, because right now I have the 1 over total resistance, so I hit the 1 over X. I end up with our total there of 55.34 ohms. Okay, so when I put these two in parallel, I end up with 55.34 ohms. Okay, I then need to keep simplifying, and so I go back to rule 1. Do I have anything in series? Yes, I do. So I can execute that first. 24 volts. And then this is going to become simplified to a single circuit here. So 2555 plus 1000 is going to be just 3555.34 ohms. Okay, so this is my R total for this circuit here, and I have two reductions. All right, so now what I'm going to do is I can start solving this one, and I'm going to work back. All right, so looking at this one, I have the voltage and I have the resistance, so I can get the current. So I is equal to V over R, which is going to be 24 volts over 3555.34 ohms. Okay, so I come here and I go 24 divided by 3555.34. I end up with 0.0068 amps. Okay, so that is my current here. 0.0068 amps is my current. Okay, so I have my voltage here, because it's a single resistor, is going to be 24 volts. 0.0068 amps is my current, and there's my resistance. All right, I'm going to take the information that I know right here, and I'm going to back up a step. I'm backing up to the step 2. Went from step 3 to step 2. Well, this is a series circuit right here. Okay, so I can apply what I know from here to the series circuit, and we've learned that in series, current stays the same. So I can carry the current from here back to here. 0.0068 amps, 0.0068 amps, because this is a single path here. There's 0.0068 amps flowing here, and there's no other paths here for this series, so any amperage that flows through this resistor must flow through this resistor. So each one has 0.0068. I can now solve for voltage drop on each one of these. So rearranging this, voltage equals current times resistance. So the first one here, I've got 0.0068 amps times 1000 ohms. And the other one here, I'm going to have 0.0068 amps times 2555.34 ohms. Okay, So if I come up here and I go 0.0068 times 1000, I get 6.8 volts. That's my first one there. So this one is dropping 6.8 volts. The second one right here is going to be 0.0068 times 2555.34. This one's going to be 17.38 volts. Okay, is what that one's dropping. 17.38 volts. Now, just for the heck of it, you see this is close to 17 and this is close to 7. So 17 and 7 is 24. So it looks like these are adding up, and according to our rules, the sum of the voltage drops here have to equal that. So it looks like we're headed in the right direction. Now, as I move back here, I can apply what I've learned in this reduction, and I can apply it to this circuit. So this 1000, well, that's a standalone. So we can just transfer the information there. 0.0068 amps and 6.8 volts, is what that resistor's characteristics are. So then going to these two, well, what do we know about these two? These are in parallel, and we know that this resistor right here represents these two parallel resistors. That's what we did this math down here for. So what can we take from here back to here? Well, for parallel, we know that voltage stays the same. Here we were able to carry the current back because current stayed the same for series, but in parallel, voltage stays the same. So we're going to bring the voltage back. 17.38 volts, 17.38 volts. Each one of these is going to drop the same amount of voltage. And so then what are we going to do? We're going to solve for current. I, once again, is V over R. I is equal to V over R. So if I come up here and I go 17.38 volts divided by 4700 gives me 0.0037 amps. Okay, and then this one right here, I'm going to go once again. I is equal to V over R. So if I go 17.38 divided by 5600 equals 0.0031. 0.0031 amps. Okay, so let's just check that real quick. So here we have 0.068 amps. That's what we determined was flowing in the circuit here, and that flowed through these two resistors, and that flowed through this first one. So apparently the 0.0068, some of it goes this path and some of it goes this path, and then it would then come back together here, and we would be back to 0.0068. Well, that means that the amperage in the top resistor and the amperage in the bottom resistor must add up to here. Let's check it. I got 0.0037 amperes running through the first one plus 0.0031. And if I look on there, it says 0.0068, which is what we had flowing through the circuit. So yes, some of the current flows through the top and a different value flows through here, but when you add them up, they equal out the total current. So as you work your way through these problems, I checked a couple of times to check to be sure the voltages were adding up, to be sure the currents were adding up, to be sure it was making sense here. And you want to do that as you work your way backwards just to be sure your calculations are making sense.